Welcome to the Deep Dive. Today, we're tackling computing, specifically the classical kind we all use, and this emerging field, quantum computing.
That's right. And our mission really is to demystify both for you. We want to lay out the key differences and, well, what makes quantum potentially so powerful.
Think of it like this. Classical computers are like supercharged calculators, following very strict rules, logical steps.
Whereas quantum computers, they sort of leverage the really strange rules of the subatomic world. It's a whole different ballgame.
And just to be clear up front, quantum isn't about replacing your phone or your laptop anytime soon.
No, definitely not. It's more like a specialized tool for really specific, incredibly complex problems that current computers just can't handle.
Okay, so our plan is to quickly touch on the basics of classical computing bits, logic gates, the CPU, just to set the stage.
And then we'll jump into the quantum stuff.
Yeah.
Superposition, entanglement, qubits. It gets a bit wild.
It really does. You're moving from definite answers, yes or no, 0 or 1, to this world of probabilities and weird connections. So let's start classically. The bit.
Right. The bit. It's the absolute fundamental unit. It can be a 0 or a 1. Think of a light switch.
Yep.
It's either off or on. That's it.
And all the information, text, images, you name it, gets broken down into long strings of these zeros and ones.
Exactly. That's binary code. And usually we group 8 bits together to make a byte, which might represent, say, a single letter.
Okay, but why binary? Why just 2 states?
Well, it boils down to electronics. Transistors, the tiny switches inside chips, are really good at reliably being in one of 2 states on or off. It's simple and dependable.
Makes sense. So you have these bits, these zeros and ones. How does the computer actually do anything with them? That's logic gates, right?
Precisely. Logic gates are the basic building blocks for operations. You have simple ones like a NOT gate, which just flips a bit. A 0 becomes 1, a 1 becomes 0.
Okay.
Then there's an A and D gate. The output is 1 only if all the inputs are 1. Like 2 switches in a series circuit both need to be on.
Got it. An OR.
An OR gate gives a 1 if at least one input is 1. But like switches in parallel, only 1 needs to be on for the circuit to work.
So by combining these really simple gates in complex ways,
you can make circuits that perform arithmetic, make decisions, follow instructions. All that complex thinking a computer does is just billions of these simple logical steps happening incredibly quickly.
Driven by the CPU, the processor, the brain.
Yep, the central processing unit. It runs through this fetch, decode, execute cycle. It grabs an instruction from memory, figures out what it means, and then carries it out.
Using things like the ALU.
Right. The arithmetic logic unit handles the math and logic operations. You can think of the CPU like a conductor reading the musical score of the program and telling the orchestra what to do.
And speed measured in gigahertz, billions of cycles per second. Modern ones even have multiple cores.
Yeah, multiple cores mean it can basically work on several tasks at the same time. True parallel processing, but still based on that deterministic bit-by-bit foundation.
Okay, so that's classical computing in a very small nutshell. Deterministic based on bits and logic gates.
But now we need to shift gears. To understand quantum computing, you really have to grapple with quantum mechanics, the physics of the very, very small.
And 2 concepts are absolutely key here, aren't they? Superposition and entanglement.
Exactly. Let's start with superposition. In the quantum world, a particle like an electron doesn't have to be in just one state, like spin up or spin down.
It can be. Both at the same time.
Sort of. It exists in the combination of multiple states simultaneously. Like a spinning coin isn't heads or tails, yet it's a mix of both possibilities.
Until you look at it, until you measure it.
Right. Measurement forces it to choose a definite state, heads or tails, 0 or 1. Before that, it's described by probability amplitudes, which tell you the likelihood of each outcome.
This is where things get strange. Schrodinger's cat territory.
It is. And this ability for quantum systems, or qubits, to hold multiple values at once is the foundation for quantum parallelism. It's like exploring many paths simultaneously.
Okay, hold that thought. What about the other concept? Entanglement.
Entanglement. This might be even weirder. You can link 2 or more quantum particles so they behave like a single system, even if you separate them by huge distances.
Linked how?
Their fates are intertwined. If you measure a property of one particle, you instantly know the corresponding property of the other, no matter how far apart they are.
That's the spooky action at a distance Einstein talked about.
That's the one. He wasn't comfortable with it, but it's real. And it allows for incredibly powerful correlations and coordination between qubits in a quantum computer. Their combined state is more than just the sum of its parts.
So a quantum computer harnesses these two things, superposition and entanglement.
And another phenomenon called quantum interference, which helps amplify correct answers and cancel wrong ones.
To perform calculations that are just, well, impossible for classical computers.
For certain types of problems, yes. Things like discovering new drugs or materials by simulating molecules, or complex optimization problems, or even breaking current encryption methods.
So it's not a replacement, but a different kind of beast altogether, built on qubits instead of bits.
Exactly. A qubit, or quantum bit, is the basic unit. Like a classical bit, it has two fundamental states we call ket 0 and ket 1, 1i.
But the key difference is superposition.
Right. A qubit can be in a state that's a combination. Alpha times 0a plus beta times 1a. Alpha and beta are those probability amplitudes, complex numbers, whose squares add up to 1.
And when you measure it,
You get 0i with a probability of alpha squared, or 1i with a probability of beta squared. It collapses to one definite state.
so let's compare directly. A classical bit is either 0 or 1, defined.
A qubit, before measurement, is a superposition of 0 and 1. Continuous possibility.
And if you have, say, n classical bits, they can represent just one specific state out of 2 to the power of n possible states at any given moment.
But n qubits, thanks to superposition and entanglement, can represent a combination of all 2 to the n states simultaneously.
That's where the exponential power comes from, this massive parallelism.
That's the potential, yes. It opens up computational possibilities that are just unthinkable classically for certain problems.
So we've gone from the clear on-off of bits to this probabilistic, interconnected quantum world of qubits.
Using quantum gates, analogous to classical logic gates, but operating on these quantum states to run algorithms.
With huge potential impact on fields like medicine, material science, AI, finance, cryptography.
Both breaking current codes and enabling new quantum secure communication. But let's not get ahead of ourselves. Building these things is incredibly hard.
Right. There are massive challenges. Keeping the qubits stable, avoiding decoherence, controlling them precisely, correcting errors.
It's a huge engineering and physics challenge. But there's enormous global investment, and progress is, well, it's happening fast. The field is moving rapidly.
Okay, so maybe final thought to leave everyone with. Consider how these quantum principles superposition, this inherent interconnectedness might offer, new ways to think about complexity and connections in our own macroscopic world.
It's fascinating. The very rules of reality at the smallest level are dictating what's possible computationally. It really makes you think.
It certainly does. Thanks for joining us for this deep dive into classical and quantum computing.